Hey everyone, Carlos here. Today we're going to take a chemical process problem and we're going to solve it using MatLAb. First of all, what is chemical process? Chemical process is an intro level class for the greater chemical engineering program. It's also known as material balance. Chemical process is a study of chemical reactions and keeping track of your inputs and outputs so you can optimize the problem. I did mention that the class is also called material balances because we have the main equation here. But for today, we're only going to worry about our in and our out. We're not going to produce anything and we're not going to consume anything. So we're going to say our input equals our output. This is due to the law of conservation of mass. So we're going to look at the ammonia production problem. Ammonia is widely used as an industrial refrigerant. Ammonia is also used in the rubber industry for the stabilization of natural and synthetic latex to prevent premature coagulation. So our problem today is going to ask us quite a few different things. And we're going to take it step by step and solve the equations. So first of all, we have our production right here. We have our fresh feed right here of nitrogen, hydrogen, and an inert gas. It's going to go into a reactor here. Out of the reactor, our products are going to be cooled. They're going to be condensed. And after condensation, we're going to separate our actual ammonia, and nitrogen, hydrogen, and our inert gas is going to exit from the top. And some of it's going to be purged, and some of it's going to be recycled back to our fresh feed and back to the reactor again. So the problem asks us to have the user input a few things. First, we need the user to input the fractional conversion of the reactor, the mole fraction of inert gas in the fresh feed, and also the mole fraction purged. We will take a base of 1 mole in our fresh feed to start off with, and later on we're going to change it. First, we're going to ask the user to enter our values of FSP, YP, and XI. Again, FSP is our fractional conversion of the reactor, XI is our mole fraction of the inert gas in the fresh feed, and YP is the mole fraction purged. After this, our program is to check that the values entered are all less than 1. We're going to run our function. We're going to solve for the moles of inert gas in the fresh feed using a mole of 1 basis of fresh feed multiplied by user entered values of XI. We're going to solve for moles of nitrogen present in the fresh feed by subtracting moles of inert from 1, total moles in fresh feed, done by assuming that N2 plus 3H2 is going to react to 2 NH3, and hydrogen and nitrogen are always present in stoichiometric proportions, which tell us there are 3 moles of hydrogen per 1 mole of nitrogen throughout the whole reaction. Next, we're going to solve for moles of hydrogen in fresh feed by subtracting calculated moles of nitrogen and inert from 1, which is our gas stream exiting condenser. We're going to enter the values of FSP and YP, which can be used to establish a relationship between fresh feed and stream exiting the condenser using variables from the mass balance. We're going to solve for the moles of nitrogen and hydrogen present in the stream exiting the condenser using calculated values from the fresh feed, FSP and YP. We're going to calculate the moles of the inert present in the gas stream using a relationship derived from the mass balance using moles of inert in fresh feed and YP. We're going to add calculated moles of nitrogen, hydrogen, and inert to get the total value of the stream exiting the condenser. We're then going to calculate the mole fractions of nitrogen, hydrogen, and inert. For our purge stream, we're going to calculate the total moles of purge stream using YP and calculate the moles of the stream exiting the condenser. We're going to calculate the moles of nitrogen, hydrogen, and inert in the purge stream using mole fractions from the gas stream. For our recycle stream, we're going to calculate total moles of recycle stream by subtracting total moles purged from the gas stream. We're going to calculate the moles of nitrogen, hydrogen, and inert in the recycle stream using mole fractions from gas stream. For our feed to the reactor, we're going to calculate the total moles of the feed to reactor, NR, by adding recycle stream and fresh feed. We're going to calculate the moles of nitrogen, hydrogen, and inert in feed to reactor by adding moles in fresh feed and recycle stream for each respectively. We're going to calculate the moles of ammonia produced, NP, by subtracting moles exiting condenser from moles fed to reactor. We're going to calculate our overall fraction conversion, FOV, using calculated values of nitrogen in feed and purge streams. We're going to end our function, and then we're going to analyze and output graphs so we can optimize our problem. So this is quite a bit, but again, we're going to take it step by step. So what this is all saying is that although we do have our difficult problem here, everything is related to each other. When you have two equations and two unknowns, you can solve for one in terms of the other and plug it in into the first equation. So this is what we're going to do, but using MATLAB. So it's going to be a lot easier than working it out by hand. So let's go ahead and jump into our code. Of course, we're going to start off with our clear screen and our close all. And we're going to ask our inputs from the user. So we're going to ask the user to input the single pass conversion, the ratio of the moles from the purged, and the moles fraction of the inert gas in the feed stream. Then we're going to make sure that all of the values are less than 1. We use the while loop to make sure that if the user inputs something that's not correct, it just goes back and asks the user to input again until the user gets it right. After we have our inputs from the user, we're going to input them into our function. Here is where our stream 1, stream 2, and our different streams are going to get solved using all the math. Again, we're going to solve for our stream 1, then we're going to use that to solve for our stream 5, then we're going to use stream 5 to solve for our individual streams of nitrogen, hydrogen, and the inert. Then we're going to move on to our stream 6, from there on to stream 7. After stream 7, we're able to go back to solve for stream 2, and then finally stream 4, because we have stream 2 and 5. So after our function does all the calculations, we're going to come back to our main code, and then we're going to graphically show our results. Let's actually go ahead and run our program now to see what our graph outputs look like. So we go ahead and run. And it asks us, enter the single pass conversion of the reactor. Let's just go ahead and do 0.3 for all of them. We entered our ratio of moles purged from the condenser and the mole fraction of inert gas in the feed stream, 0.3 as well. Here we go. So we have our three figures, which graphically show the relationships of the streams to each other. Figure 1 shows the ammonia production with varied purge stream. Figure 2 shows the ammonia production with varied single pass conversion. And figure 3 shows the ammonia production with varied inert gas feed stream. Let's go ahead and minimize this. And part of our outputs was an actual written analysis of our ammonia process that we chose. The relationship of ammonia production with a varying purge ratio is the power function NP 0.24 times YP to the negative 0.35. The relationship of ammonia production with a varying reaction single pass conversion is the following. And the relationship of ammonia production with varying mole fraction of inert gas in the feed is the linear function as followed. From the graphical analysis of the system, the purge ratio should be minimized. From observed figure 1, the least moles purged yields the greatest moles of ammonia produced. However, it should not be 0 because it is useful to prevent the accumulation of inert gas in the process. The reactor single pass conversion should be maximized. The greater conversion of reactants by the reactor will yield a greater amount of ammonia produced. The mole fraction of inert gas in the feed should be minimized. The less amount of inert gas present, the more ammonia is produced. However, it is a linear relationship, so a greater amount of inert does not affect production like moles purged. The theoretical amount of ammonia produced after optimization of the process is 0.988 moles compared to 0.412 moles produced from other inputs. Let's go ahead and kill, and let's run it again. Enter the single pass conversion. If we try to put 2, let's say 3 and 4. Again, it says entered values must be positive and less than 1. Please enter new values. So this is part of our checks and balances that we did into our code, into our loop. It will keep asking the user for inputs as long as they get it wrong. Again, they must be positive and less than 1. So we can do, again, 0.3, 0.123, and 0.9. And we get our answers. This code works great and is very flexible. As you can see, it works for different types of reactors, different purge ratios, and different streams. But unfortunately, one limitation of this code is that we need to be given the specific knowns. Without knowing what our fraction of conversion of the reactor is, what our mole fraction of the inert gas in the fresh feed is, and what our mole fraction purged is, this code does not work. If we are ever giving different knowns, we just have to write up a different code with those knowns, tweak it up a little bit, and we'll be able to run it for the knowns given. We actually wrote up our code to ask the user how much was inputted at the beginning. First, we ran the program with a base of 1, and now we're asking the user how many moles were actually inputted, and to reanalyze the whole process. So let's say we are going to input, instead of a base of 1, we're going to input 400 kilomoles in our fresh feed. So then that gives us the total cost. The total cost to cool the gases exiting the reactor and condense the ammonia from 400 kilomoles to the fresh feed is almost $230,000. The problem gave us the temperatures leaving the reactor and leaving the cooler. It also gave us the heat capacity of joules per mole Kelvin of nitrogen, hydrogen, and our inert, and the heat of vaporization for ammonia. The cost of cooling is $17.68 per million joules. And when we plug that into our function of cost, we can see that our total cost for this was $230,000. If we go back to our main code and run it again, let's go ahead and just run the second part. And the total kilomoles from the fresh feed, let's say instead of 400, let's just do 20 kilomoles. Our total cost is going to be just $11,000. We also created a menu to ask, would you like to enter new variables? If we click yes, we start the whole thing over again. Until the user says, no thank you, we are done with our ammonia production. This program would really help to minimize the cost of production of ammonia while also maximizing the actual process of ammonia. Well, thank you everyone. I hope you enjoyed this video, and I really hope you learned something today.